Hi guys, welcome to the last section of Unit 1. And what I want to do today is go ahead and talk a little bit about light and properties of light, as well as a little bit of physics stuff right toward the end. But other than that, that will go ahead and finish us up with Unit 1. Which means, guys, you're probably going to have a test coming up pretty quickly. So check Blackboard and find out what information's up there and exactly when your first test is scheduled. The picture you see on the screen right now is just a nice picture of the sun. Well, remember, guys, that's where we get all of our light. Remember that we're not going ahead and actually producing light on the Earth. The reason that we see the sun is because it actually is producing light. So what is that light and what's going on? So let's talk about some waves and light. Okay, so guys, a wave is a movement of energy. Yeah, you look at this and you've definitely got that water wave right there. Think about the energy that you've got associated with that water wave. And we're basically going to spend most of our time on light waves, but realize there's all kinds of other waves out there. A nice flag waving in the wind. Two types of waves, mechanical waves and electromagnetic waves. Mechanical waves are waves that require a medium to travel on. And that's probably going to be all the kinds of waves that you're familiar with. We think about sound wave, they have to have the air to go ahead and travel on. Think about earthquake waves, they travel through the ground. Well, electromagnetic waves, on the other hand, do not require a medium. They will travel through a vacuum. Within the types of waves, there's two different types of wave movement. One of them is called a transverse wave, and the other one is a longitudinal wave. Transverse waves are the ones you're, again, probably more familiar with. It's that up and down movement, where they are moving perpendicular to the direction of motion, whereas longitudinal waves are moving parallel to the direction of motion. Probably the best examples everybody gives of transverse waves are water waves or light waves, and then for longitudinal waves, looking at sound. And then we have this twisting wave, which is called a torsional wave. Hey guys, what I would like for you to do is go ahead and check out these websites that give you a chance to work with waves a little bit and to see what happens with them as you change various amplitudes, things like that. So go ahead and pull these websites up after we finish class and see what's going on. You'll also have these repeated for you on Blackboard, and I've just got a list of those websites as well. Wave characteristics will go with any wave, whether they're talking about a longitudinal wave, a torsional wave, or a transverse wave. And so the first thing I want you to know about is a wavelength. Then we've got the period and the frequency. And notice, guys, I have equations back there. I'm not going to expect you to know those equations, but I do want you to realize that frequency and period are going to be the inverses of each other. Then we've got amplitude, which is a measure of the energy. And then we can talk about the speed of the wave. And there's two forms of that speed. We can either talk about wavelength times frequency or wavelength over the period. Now, we need to go back and define exactly what these terms are. So if I think about what a wavelength is from one point on the wave to where it starts over again. And the wave that you see right here is a transverse wave. So we've got a crest and we've got a trough. Crest is kind of like the top of the wave, whereas a trough is the bottom of the wave. Or if you're into standing on your head, guys, then it's a trough is the bottom part or the top part of the wave, and crest is the bottom part of the wave. Just kind of depends on how you're looking at that. So I've got a wavelength from crest to crest, or from trough to trough, or from one point on the wave to where I start over again. Now, guys, I want you to look at this diagram and go from crest to trough. Do I have a full completed wavelength? And the way that you try and answer that is say, okay, am I at the same point where the wave is starting over again? And so obviously, guys, we're not. Because if I'm at the crest, then the next thing I'm doing from the crest is I'm going down. If I'm at the trough, I've got to go up. Well, that means we're not at the same place. So remember, the wavelength is defined as the point distance from one point on the wave to where the wave starts over again. And wavelength is measured in a length unit. A lot of times it's meters, it could be centimeters, it could be feet, whatever. Now, the other thing I want you to know on this picture is we can talk about the period of the frequency, and the period is a time for one wave to pass a given point in a given time. Or we can talk about the frequency, which is a number of waves going past a given point in a given time. And like I said, guys, they are simply inverses of each other. And then the amplitude defines how tall the wave is, which is another way of looking at the amount of energy that is associated with that wave. Obviously, the greater the energy, the greater than the height of the individual wave is going to be. Now, there are several properties of waves I want you to be familiar with. One of them is reflection. refraction, diffraction, interference, the Doppler effect, dispersion, and polarization. So let's go back and talk about what reflection is. Reflection just simply means that I have a wave that hits a barrier and it bounces back. Bouncing back of a wave from hitting a barrier. Okay, think about the fact that you're in an empty room. Okay, you know that empty room just feels differently. Well, that's because there's nothing in that room to go ahead and absorb the sound energy, and so that energy hits the wall and bounces back. Okay? If you play pool a lot, you've also taken advantage of reflection. If you've looked in a mirror, you've taken advantage of reflection. And when we talked last time about mirrors and looking at telescopes, well, their telescopes were made from mirrors, and so you're talking about the light bouncing back from that mirror. Now, compare that with refraction, which means I have the wave that's going to be bent due to the fact that it changes mediums. Going from air into water, from air into maple syrup. It doesn't really matter. You're just going from one medium into another. And diffraction is bending of waves around a barrier. Interference is what happens when waves actually run into each other. And we find that when they do that, their energies add. And energy is a measure of the amplitude of the waves. And so that energy, how tall those waves are, then go ahead and add when we have waves crossing each other. The Doppler effect is an apparent, and guys, I want you to underline that word apparent, because it's not an actual change, it's an apparent change in frequency of the waves due to either the motion of the source that's producing the waves or the observer, that might be you looking at that waves, or both. Now, dispersion, on the other hand, is spreading the waves out, and then polarization is where you are talking about the alignment of the waves and the oscillations that they undergo. Another way of thinking about polarization is thinking how all those waves are aligning themselves as they go through a particular medium. So, let's go through some examples. Now, what you see right here on the screen, and I know it's kind of hard to see at the bottom, but you've actually got a curved piece of glass. Okay, now think about what kind of glass this is from when we talked about telescopes last time. Is this a concave surface or is this a convex surface? Well, hopefully you realize that this is a concave surface. So we're talking about a mirror. Okay, so I know it's hard to see, but it is mirrored on one side. The light comes in, and it goes ahead and is reflected back. You can see the red beam, you can see the blue beam, and you can see the green beam. And you can see that each one of them are reflected back. And if you look really closely at the color of where all three of them are overlapping, that's a nice white color, so that we know when we add all the colors of the rainbow of the spectrum, we have white light. Okay, so after you look at this picture, we're talking about reflection from a nice curved surface. Now, here is just a nice barrier, and you can really see if we take that surface you were just looking at that was curved and we flatten it out, then you've got a nice wave that's basically hitting a barrier and reflecting it back. Okay, notice, guys, I've got a line right down the center, and that's called our normal line. Okay. A normal line is simply a line that is perpendicular to the surface that the wave is hitting. And we talk about the angle coming in is equal to the angle going out, or the incident angle is equal to the reflected angle, and so I've got that marked on there. You can see angle I and angle R. So incoming angle is equal to the outgoing angle, and that's called the law of reflection. Angle I is equal to angle R. I kind of like this picture of reflection. A nice, smooth, reflected surface off of the lake out there. Which, by the way, guys, I wish that was my home just out there in that nice, beautiful lake. But you're getting that reflected image. Incoming angle of light is equal to the reflected angle. Now, refraction, on the other hand, is that bending of waves due to the fact that you change mediums. Now, if I go from one temperature to air of another temperature, that really is talking about changing that medium as well, because we're changing the density of the material. And that boundary is going to go, or the bending of that light is going to occur at the boundary. And I've got a website there, which again is listed on the Blackboard site, that I want you to visit, and it gives you a chance to kind of play with some refraction and what happens when you change the material that light goes from one into the other. Now here's a picture of using those same kinds of pieces of glass, only now we're talking about the light going through the glass, so it's being refracted instead of being reflected. Now, the first one on the left is just nothing more than a flat piece of glass. You don't have any kind of curved surfaces whatsoever. But you can definitely see that it is refracted, and you can see that the refraction occurs at the boundary. Now, it comes out of that nice flat piece of glass, and it goes through a concave lens. And you can see that, if you look really closely, it goes ahead and it is spread out. Remember that a concave lens is a diverging lens. And so you can see that the blue light pretty well passes straight. But if I look at the green and the red, they indeed are bent outward just a little bit. And if you can kind of use your imagination and follow it all the way back, you can see where they're going to cross each other on the left side. Okay? And now I've got all three of them coming out of my concave lens, and they're going to go through a convex lens. Now, unfortunately, that's where my picture ends. So, unfortunately, you're not seeing that complete light coming out of that convex lens. But you can see that they are going to start coming toward that point then. So this just gives you a feel for what happens when you go through a flat piece of glass. You go through then the two different types of curved surfaces, a concave lens and then the convex lens. Remember, guys, we talked the other day, your eye is like that convex lens. Now here's a refraction, only now we're going through a piece of glass that does not have parallel sides. This is a prism. Notice that I've got white light coming in off the left, and when I do that, it's going to break apart into its component colors, because every color then gets refracted just a tad bit differently on that one side, and so you spread it out and you form a rainbow. So red, orange, yellow, green, blue, and violet are the colors of the rainbow. And remember that because we're going to come back and talk about light a little bit more and come back and talk about visible light and the order of the colors in the rainbow. Again, another website I'd like for you to go look at. Now we can talk about dispersion. Remember I said dispersion was basically taking that light and just spreading it completely out. Okay, and guys, this is what you want to give your significant other, and this will make them a very happy camper. Or ladies, maybe that's what you want to give your significant other. But anyway, you got a really nice diamond there, and one of the things that you look for in a diamond is the ability to spread that light out. Because you want that diamond to go ahead and sparkle. And simply because of the way that the diamond itself is cut. But for our purpose, this is taking that light and spreading it out. And notice that you get that spectrum of color then as you're looking at the light. Diffraction is the bending of a wave around a barrier. Now, remember guys, we're going around a barrier. We're not going through a material or anything like that. So the material that the light is actually traveling in is going to remain the same. It just happens to bend around a barrier. Look at the back of a CD. You can see those nice diffraction patterns. Some of you may not have actually seen a razor blade. These are the old razor blades. Okay, and this is taken from a light that's looking down at that razor blade, and so it's going through. And not only are you seeing the light then that is diffracted around the actual laser blade itself, which is a very, very thin piece of metal, but then you're seeing interference patterns within that. And that's what those light and dark areas are, both on the sides and then especially through the center of the the razor blade. Doppler effect, remember, is an apparent change in the frequency due to somebody moving, either the source moving or you moving. The object is coming towards you. You hear an increase in the frequency of the sound or the light or whatever happens to be the wave. And if it's going away from you, there's a decrease then in the frequency. And I'd like you to try something. Okay, after you finish this, done with this section, go in, take a nice tall glass, put it under the faucet in the kitchen. Then I want you to close your eyes, and I want you to turn the water on. And I want you to listen to the sound that the water makes as that cup goes ahead and fills up. And I think whether you're looking at it or not, you're going to realize when that water reaches the lip of the cup, and you can turn the water off before then it overruns. And so you're looking at an example of the Doppler effect, that increase in frequency as that wave is coming towards you. In this case, we're talking about that sound wave that's being reflected off of the surface of the water as the water level is rising. Most of you are familiar with the sound of a train is coming towards you, you get an increase in frequency. When it goes away from you, you get a decrease in frequency. Well, we can do the same thing in light, and it kind of shows you what happens as the waves go ahead and bunch together. And so you see that increase in frequency compared to then what happens when they kind of leave those waves behind because of the motion, and you get that decrease in frequency. Now, we will come back to this picture later on when we talk about black holes, but this is also the Doppler effect dealing with light. Now, if you think about the fact that you have an apparent increase in frequency when the sound is coming towards you, let's do an increase in frequency when the light is coming towards you. And so everything tends to get blue shifted. And so that's what I see on the left. I've got light that is coming toward me, and so that's why you see it as blue shifted, the color blue coming towards you. On the right side, it's going away from me because this is spiraling around the material and being pulled into a black hole. And so it's spiraling as it's doing that. And so the left side is coming toward me. The right side is going away from me. And so the right side then is red shifted. Now, we're going to also come back to that in the very last section when we talk about cosmology, when we talk about galaxies that are billions of light years away. And we can tell that by looking at the redshift of their spectrum. Extremely redshifted, which tells me that they're extremely far away. Again, a couple of more simulations online that I'd like you to go ahead and check out. And then we've got interference, and that's what occurs when one wave passes over another or passes through another. And so when waves cross, their energies add. And we can either call that adding as constructive, which means I'm increasing the wavelength of the wave that's being produced from when the two cross, or destructive, which means that I'm basically going ahead and destroying that wave when they cross because it will have a smaller amplitude than it had before. All of you guys have seen water petals and going ahead and interfering with the surface of the water. Well, let's look at what that really means. When I have two waves, and you can see here I have wave 1 and wave 2, notice when they add, or when they meet, their energies add, and so you get the wave then that's on the right. Notice the increased amplitude. Okay? That's constructive interference. My amplitude after is bigger than my amplitude before of my waves. Destructive interference, on the other hand, is when, like I said, that amplitude is smaller, and I think you can see here those two waves are completely out of phase with each other. And so you get a nice straight line, which tells me that when they've added together, they have basically canceled each other out. And so that's why I indeed get that straight line. Now, as soon as the waves then would go ahead and continue passing through each other, you haven't destroyed the waves. All you're looking at is how that energy is added as those waves have passed through each other. So as soon as they pass through each other, they're going to pop back up with the types of waves that you see here, 1 and 2. Then we can talk about polarization. And polarization, like I said, is defining the orientation of the wave as it's going from one material into the other. And so it depends upon the direction that that light is entering the material. Now, this is a real good example of polarization. I've got two pieces of Polaroid film, and I've crossed them at 90 degrees. So one of them, okay, in your mind, take those two apart. One of them allows waves that are going through that have waves of one orientation. And the second piece has waves of the orientation that's at 90 degrees to that, and allows those waves to go ahead and pass through. So when I put them at 90 degrees to each other, I've basically canceled out any of the waves, so I don't see anything coming through. If you've ever used Polaroid glasses, things like that, well, that's the type of thing you're doing. You're simply defining the orientation of those waves coming through the Polaroid glasses, and you're canceling those waves out because of the way that you're putting that Polaroid film in there. So now let's talk about what is light. Because we've talked about light in terms of waves, but the kinds of characteristics of waves, like I said, go for every other kind of wave that's out there. We want to just talk about what light itself is. And remember, guys, when we talked about waves, I said one wave was a mechanical wave, one wave was an electromagnetic wave. Well, electromagnetic wave is radiant energy that goes ahead and stimulates the rods and the cones in the back of your eye. So that's actual energy that has to enter your eye that stimulates the rods and the cones in the back. And for us to see in visible light, then we're talking about a wavelength of about 3,900 angstroms to about 7,700 angstroms. And an angstrom is just a unit of distance. And we know that light in a vacuum travels at 186,000 miles per second. Okay, exactly 186,300 miles per second. Round that off to 186,000 miles per second, and you should be fine. Now, that's in the English system. So that means, guys, that if I talk about light in 1 second, light will travel 186,000 miles. So, guys, I want you to realize that's going pretty fast. If we look at that number in terms of the metric system, then we're talking about 3 times 10 to the 8th meters per second. Either way, guys, light is traveling extremely fast. And in fact, light is the fastest known thing to travel. We have a cosmic speed limit. That is the speed limit of light. Nothing can go faster than the speed of light. So we know light can be thought of having characteristics of both waves and particles, and we're not going to get into that particle part of waves. But I think about a photon. Think about when we talked about the atoms and a photon jumping up to an outer energy level, and that energy then is given off when the electron jumps back down. So light can either be thought of a wave or as particles. For what we are doing mostly right now, we're going to think of light as a wave. So we can talk about something called the electromagnetic spectrum, and it's a spectrum of light that travels at the speed of light in a vacuum. And remember, guys, I'm always very careful to say, when we talk about that 186,000 miles per second or 3 times 10 to the 8th meters per second, talk about that as in a vacuum. Because when we start entering material, whether it's air, although essentially for air it's the same thing, but if I look at glass or I look at water or those kinds of things, then the speed of light is going to slow down. So as it travels through a particular material, then the speed of light will slow. There's all kinds of ways that we can measure that. We talk about the index of refraction of a material. That's going to give us a feel for what the speed of light is in that material. As far as you guys ever having to worry about doing that, I'm not. But I do want you to realize that when it goes through a particular material, it will go ahead and slow down. The only time it's really traveling at the speed of light is in a vacuum. So basically, light is a beam of electromagnetic radiation traveling in a transverse wave. So let's talk about the electromagnetic spectrum. Okay, guys, if you look here, it is a spectrum. It's one wave that just kind of feeds into the other. I mean, I've got this labeled very distinctly in terms of, this is ultraviolet, this is visible, this is infrared, but it's really just one bleeds right into the other. Okay? Now, if you look on the left side, okay, so where we're talking about radio, the other thing I want you to put down on your notes is I want you to put down that that is very low energy, very long wavelengths, and very low frequencies. Long wavelengths, very long, okay, very low frequencies, and very low energy. Okay, so if I look at the wavelength, we're talking about wavelengths in the form of 10 to the 3rd meters. Okay, we're talking about frequencies of 10 to the 4th. Now, I know that sounds kind of high, but compared to what we're looking at with gamma radiation, 10 to the 4th is an extremely low frequency. Now, notice what my frequency is labeled as. It's labeled as hertz, Hz. You're probably more familiar with hertz in terms of cycles per second or waves per second. Okay, well, we can also talk about seconds to the -1 for a frequency. There's a number of ways that you can look at actually specifying what your frequency is. Now, let's go up so that the other end of the spectrum, where I've got those gamma rays, are very high energy, very short wavelengths, and very high frequencies. And then we've got our electromagnetic spectrum in between. So let's go back down to the radio waves, lowest energy, okay, lowest frequency, and really long wavelengths. As I start moving up, I go from the radio part of the electromagnetic spectrum, a little bit more energetic, okay, and you can see that those are called microwaves, same kind of microwaves you talk about when cooking your food. Okay, and look at what my frequency is doing and looking at what my wavelengths are doing. Also, the picture in the center kind of gives you the idea that you're starting out with those longer wavelengths, and then we're going to get really short. Okay. Now, guys, you will need to know the order of the electromagnetic spectrum. I don't care whether you know it from the low energy to the high energy or high energy to the low energy, but that is something you will need to be aware of, is what is the order of the electromagnetic spectrum. So radio waves, a little bit more energetic, I get to microwaves. Then I get up to infrared waves, and that's basically heat. Visible, which is what we see, so that's about 10 to the minus 6 meters. An angstrom, guys, remember what we were talking about before, is about a 10 to the minus 10th meters. So that's where you're getting those difference in those numbers. Then ultraviolet, then X-rays, and gamma rays. And I'm sure most of you have had an X-ray, so you know the X-rays then go through the fleshy part of your body, but it won't go through the bones. Gamma rays will go straight through you without any problems at all. Then if you see the corresponding numbers down at the bottom for the frequency, we're talking about gamma radiation, we're talking about frequencies of 10 to the 20th, X-rays, frequencies of about 10 to the 18th, and so on. Would I ever expect you to know those numbers? Nah, absolutely not. The only thing I expect you to know is the order relative to the amount of energy. And once you know it relative to the amount of energy, then you also know it in order of wavelength and also in order of frequency. Now, here's another version of the electromagnetic spectrum. Same kind of thing, only this time you have images at the bottom, and they give you a feel for really the size of that wavelength. If I look at a gamma ray, all the way over on the right, notice that that wavelength is the size of an atomic nuclei. And that's really, really small, guys. Whereas if I go all the way down and look at a radio wave, then I'm talking about wavelengths the size of buildings. Okay, think about what we talked about last time with the telescopes. You had those big telescopes that were the radio telescopes. They were the size of big buildings, or being built in the side of the Earth itself. Well, that was because those wavelengths they're collecting are so much bigger. Where if I look at the visible light, okay, guys, our wavelengths in the form of a little protozoan. If I think about ultraviolet light, its wavelength is the size of a molecule. So that just gives you, I think, a little bit better feel for what the wavelengths are when you look at actual things. So now let's talk about the individual types of waves. What I have here is a gamma wave. Now, I know you probably can't tell that for right now, but if I look at that picture on the left, I'm really looking at a picture of our universe, and the line that comes straight across is actually our galaxy itself, looking at the spiral arms of our galaxy. And it's extremely bright in gamma radiation. Okay? Gamma radiation, the white part is going to be really hot. Well, notice what's going on in that upper left. You have a gamma spike, and that occurred in a very, very short period of time, less than about 10 seconds. And that was one of the most powerful explosions that we have ever seen of gamma radiation. Exactly what happened there, we're not exactly sure. But we know that there was a burst, probably some kind of supernova or something happened in a galaxy, that produced that gamma radiation. And you can see that it really, at some point, completely outshined essentially the rest of our galaxy. And remember this picture when we come back and finish up, because we'll talk about the gamma radiation in those galaxies. This is a living skeleton. So this is looking at X-rays now, and I would certainly encourage you to visit this website. It's the Access Excellence website, and when you pull it up, guys, what you're going to have is a skeleton right there, and it's going to give you a chance to look at some of the X-rays of that skeleton. And go look at the arms or the head or the legs or the hands or something like that, and then give you the X-rays of that particular part of the body you're looking at. One of the neat things about this website is it also will show you the image before, and then it will show you that X-ray image then labeled. There's also one of an arm right there that you see the arm, you see the flesh actually on the arm, and you can tell that that arm just really doesn't look good. And then you see the X-ray of that arm, and you realize that there's been several bones that were broken within that arm. Okay, now what is this one? Well, guys, if you're a Star Trek The Next Generation fan, you recognize this as Geordi. Kind of looks different, doesn't it? In one of the episodes, you had Geordi that was being turned into this creature that gave off ultraviolet light. So that's what you see right here, Geordi giving off ultraviolet light. And it's not going to be visible to our eyes, but it certainly is to instruments. Think about black lights. Okay. ever been in a cave and they've shown you some of the crystals down at the cave, and they turn all the lights off and then turn on this black light, and you can see the fluorescence and phosphorescence of the rocks in the cave itself. And of course, white light, that's coming through a prism. So white light comes in, you break it apart into component colors, which talks about then the visible light that we see. So guys, what do you see here? Seems to me just like a nice ordinary fuse box. Okay, and if I look at it, I can't really tell that there's anything wrong. But if I look at it using infrared radiation, I can tell that part of it is a lot hotter than what the other parts are. Well, that tends to be a problem. So what's going on there? Why is that heat being produced? Certainly can't tell that it's there visibly. Now, if I put my hand there, I could certainly tell that there's more heat coming off. But you have to go figure out what's going on. And now here's a picture of a person. So that's what you look like in infrared light, guys. Now, what's the hottest part of your body there? What's the coolest part of your body? Well, you can see the temperature on the right there. 94 degrees Fahrenheit, that's kind of red, and the orangish part, or excuse me, the violet part then is a little bit cooler. But you can see the nose, you can see the lips tend to produce a lot of energy. You know, so if you're thinking about being outside in the cold, you know, what do you want to cover? Well, generally the extremities tend to give out more energy. You tend to lose energy through your extremities. And so you want to make sure all those are really covered well. This will also show up if you have any kind of injury, because if you have, let's say, a leg injury and you've bruised it, or you've sprained let's say, a tendon or something like that, that will show up because there tends to be more energy right there because the body itself is trying to heal that. And so if you take a thermal scan of yourself, you can sometimes tell where you have injuries. And now if we look at just the background radiation in terms of the gamma radiation of our universe, this is kind of what we get. It gives you a feel for that background radiation that's spread all the way out throughout our universe. You will see this picture later on when we come back to what's going on with our universe itself. And just kind of remind you of what those radio telescopes look like. Now, there's three different types of light spectra I want to talk about. One of them is called a continuous, one of them is emission, and one of them is absorption. Continuous spectrum is one that you get from either a solid or a liquid, and it gives you a continuous red, orange, yellow, green, blue, and violet spectrum. Emission spectrum gives you a bright line spectrum. It means energy is given off. That means my electrons are going from a higher energy level down to a lower energy level. And absorption is what happens when those electrons absorb that energy. And so I'm going to then have places in my spectrum where energy is gone. And that means that the electrons have jumped up to an outer energy level. Then spontaneously they will give that energy off, and I will then regenerate that emission spectrum, or that bright line spectrum. So let's take white light, put it through a prism. And that's where I'm going to get that nice continuous spectrum that you see on top. Then the middle spectrum is what happens if I would take a continuous spectrum and put it then through a gas or something, and the gas then is going to go ahead and absorb that energy out, okay? And that's what you're going to see at the bottom, an absorption spectrum, okay? Just dark lines because of the fact that you have energy missing there. And then when that bottom spectrum then, the electrons have absorbed that energy, the electrons have jumped up to an outer energy level, they will spontaneously then give off that energy, and you will generate that bright line spectrum that you see in the middle. Notice, guys, that the bright line spectrum is exactly the same spectrum that the energies then were absorbed out by the electron. Okay? We'll come back to that a great deal when we talk about analyzing stars and analyzing galaxies and looking at what's happening. This is kind of basically showing what I just talked about. You can see that continuous spectrum. There you see some hot gas. It goes to a continuous spectrum. It then goes ahead and gives off those bright lines. And then you can see the continuous spectrum there. It went through a cloud that was cold. It absorbed those energies out. And that's where you got your dark bands, or simply areas in the spectrum that are missing. So with that, guys, that kind of gave you a feel for properties of waves and then light in general, and then looking at specific properties of light that we will use then to go ahead and talk about the rest of the semester. So with that, guys, this finishes Unit 1. Please make sure you've checked Blackboard, you've downloaded the review, and made sure that you've done everything on Blackboard that you need to get done for Unit 1. Otherwise, guys, have fun and do really well on that test. See you later.